Welcome to G Fun Facts Online, where we explore the deepest mechanisms of our cosmos. Today, we are not looking at the universe merely as a vast expanse of space, but as a laboratory of extremes. We are entering a domain where the familiar laws of physics play out on scales that defy human intuition, creating worlds that challenge our fundamental understanding of planetary formation. We are talking about the intersection of two of astrophysics' most dramatic phenomena, the crushing, shape-shifting power of gravitational tidal distortion, and the silent, deep-pressure alchemy of carbon crystallization. We are talking about carbon planets. To understand how a planet becomes a diamond, we must first deconstruct the architecture of these worlds, beginning with the elemental ingredients. In our own solar system, the chemistry of rock is dictated by oxygen. Earth, Mars, and Venus are silicate worlds. This is because, in the protoplanetary disk that birthed our sun, oxygen was the dominant heavy element. It bound avidly with silicon, magnesium, and iron to form silicate rocks. However, the galaxy is chemically diverse, and the fundamental determinant of a planet's mineralogy is the carbon-to-oxygen ratio, or the C/O ratio, of its primordial nebula. The dividing line is a ratio of roughly 0.8. In systems like ours, where the ratio is lower than 0.8, oxygen is abundant. It oxidizes all available carbon into gases like carbon monoxide and carbon dioxide, leaving the remaining oxygen to form silicates. But in systems where carbon outnumbers oxygen, where that ratio climbs above 0.8, the chemistry flips entirely. Oxygen is rapidly consumed to form carbon monoxide, leaving a massive surplus of carbon. This excess carbon cannot form gas. Instead, it condenses into solids. In this environment, the rocks are not silicates like olivine or pyroxene. Instead, they are carbides, such as silicon carbide, and pure carbon allotropes like graphite and diamond. Astronomers have identified two primary pathways for the creation of these carbon-rich bodies. The first is the carbon-enriched disk scenario. These are planets forming around stars with naturally high carbon abundances, often asymptotic giant branch stars or specific populations of red dwarfs. Here, the dust grains coagulating into planetesimals are composed of graphite and silicon carbide. The second pathway is far more dramatic and involves the death of a star. This is the white dwarf pathway. When a massive star creates a pulsar, or a sun-like star evolves into a white dwarf, the core remains rich in carbon and oxygen. If such a remnant exists in a binary system, the outer layers of the star can be stripped away by the companion's gravity. What is left behind is a naked, ultra-dense core. This object is essentially a crystallized stellar ember, a planet born not from dust, but from the heart of a dead star. Once such a world is formed, it is often subjected to the tyranny of the inverse cube law of tidal forces. Planets orbiting close to their stars do not exist in peaceful isolation. Gravity is not uniform. The side of a planet facing its star experiences a stronger pull than the center, and the center experiences a stronger pull than the far side. This differential force creates a stretching effect along the line connecting the two bodies. On Earth, the moon's pull raises the oceans by a few meters. But for a massive carbon super-Earth orbiting close to its host, the star's gravity can raise tides of solid rock kilometers high. This leads to ellipsoidal deformation. When these forces become extreme, the planet ceases to be a sphere. It is pulled into a triaxial ellipsoid, a shape resembling a rugby ball or a lemon. This is known as a prolate spheroid, where the longest axis of the planet points directly at the star. There is a dangerous threshold known as the Roche limit. If a planet gets too close, the tidal forces overcome the planet's own self-gravity, the force holding it together. At this point, the planet disintegrates, forming a ring system. Many carbon planets we observe exist dangerously close to this limit. They survive only because their high density, owed to diamond and tightly packed carbides, gives them immense structural integrity. This proximity comes with a cost: tidal heating. If a planet's orbit were perfectly circular and tidally locked, the distortion would be static. However, most orbits have a slight eccentricity, meaning they are oval-shaped. This creates a pumping action. As the planet moves closer to the star at periastron, the gravitational grip tightens, stretching the planet further. As it moves away at apoastron, the gravity weakens, and the planet attempts to spring back to a sphere. This constant rhythmic flexing, stretching and relaxing, generates friction within the planet's mantle. Rock grinds against rock on a microscopic scale through a process called viscoelastic dissipation. This energy dissipates as heat. In extreme cases, this tidal heating can be more powerful than the heat from radioactive decay, turning the mantle into a magma ocean and driving violent volcanism. This brings us to the core conflict of these worlds: the diamond anvil. The journey from carbon to diamond is a story of pressure and temperature. Carbon is a polymorph. It can exist in different crystal structures depending on conditions. At low pressures, like on Earth's surface, carbon atoms arrange in hexagonal sheets to form graphite, which is soft and opaque. But as pressure rises above approximately 4 gigapascals, the atoms rearrange into a cubic lattice, where every atom is bonded to 4 others in a rigid tetrahedron. This is diamond, the hardest known natural material. At even more extreme pressures, predicted around 1000 gigapascals, conditions found in the cores of super-Earths, diamond may transform into even denser, potentially metallic phases known as BC8. For a planet to have a diamond mantle, it needs to be massive enough to generate the requisite internal pressure. On a planet with 2 to 10 times Earth's mass, the internal pressures are immense. If the composition is carbon-rich, the mantle is not made of flowing silicate rock, but of solid or viscous diamond. However, crystallization requires the material to be cool enough to solidify, and tidal distortion generates immense heat. This creates 2 scenarios. The first is the molten scenario. If tidal heating is too intense, the carbon may remain liquid. Liquid carbon is a strange beast. Experiments suggest it acts like a metal and is less dense than diamond. A planet with a liquid carbon ocean would not be a diamond planet in the static sense, but a world of black, metallic seas. The second is the crystallized scenario. If the planet can dissipate heat efficiently, or if the tidal forcing settles down, the interior cools. Under the crushing weight of the overlaying crust, the carbon lattice locks into place. The result is a planetary-scale crystal. Let us examine the specific worlds where these forces collide, starting with PSR J1719-1438b, often called the pulsar's gem. Discovered in 2011, this object is the archetype of the diamond planet. It orbits a millisecond pulsar, a neutron star spinning 10,000 times a minute. The planet orbits incredibly close, completing a year in just 2.2 hours. PSR J1719-1438b is likely not a planet in the traditional sense. It is believed to be the remnant core of a white dwarf star. The pulsar's gravity stripped away 99.9% of the star's original mass, mostly hydrogen and helium, leaving only the dense carbon-oxygen core. Because white dwarfs are degenerate matter, they cool over billions of years and crystallize. This world is essentially a diamond sphere, 60,000 kilometers across, 5 times the diameter of Earth, but with a mass similar to Jupiter. Its density is at least 23 grams per cc, far denser than platinum. Orbiting so close to a pulsar, a normal gas giant would be ripped apart. Only the immense tensile strength and density of crystalline carbon allow this world to survive the tidal forces. Next, we look at 55 Cancri e, the lava-diamond hybrid. Located 40 light-years away, this super-Earth orbits a sun-like star. It orbits so close that its surface temperature exceeds 2,000 degrees Celsius. Early density estimates suggested a carbon-rich interior. While recent data from the James Webb Space Telescope hints at a volatile atmosphere and a potential silicate mix, the carbon planet hypothesis remains a potent model for its interior dynamics. 55 Cancri e is tidally locked. The day side is a permanent magma ocean, while the night side is solidified. The tidal forces here are not breaking the planet, but they are heating it. If the mantle is carbon-rich, we might see a graphite crust floating on a diamond magma slush. Furthermore, diamond has the highest thermal conductivity of any geologic material. A diamond mantle would transfer heat from the core to the surface with terrifying efficiency, potentially creating a unique tectonic regime where the planet cools much faster than a silicate world. Our third case study is PSR J2322650b, the Lemon World. A more recent discovery, this planet orbits a millisecond pulsar and exhibits extreme tidal distortion. Observations and models suggest the planet is significantly deformed, shaped like a football. Unlike normal gas giants, its atmosphere is devoid of water but rich in carbon species, hinting at a carbon-dominated interior. This planet perfectly illustrates the connection we are discussing. It is a carbon world, undergoing visible tidal distortion. The internal pressure created by this distortion likely creates a complex zoning of crystallization, perhaps a diamond core that is needed by tides, generating heat that keeps the outer layers liquid or gaseous. How do we detect these diamond worlds and their distorted shapes? Astronomers use several ingenious methods. The first is observing ellipsoidal variations. When a football-shaped planet orbits a star, it changes its cross-section relative to the observer. When we look at the broadside, it reflects more light. When we look at the pointed end, it reflects less. This subtle brightening and dimming, separate from the transit eclipse, allows astronomers to calculate the Love number, a measure of the planet's rigidity. A solid diamond planet will deform differently than a gaseous or silicate one. The second method involves thermal phase curves. By using infrared telescopes like the JWST, we can map the heat distribution. A diamond planet, with its high thermal conductivity, might show a smaller temperature difference between day and night compared to a silicate planet, as the heat is rapidly shunted through the crystalline interior to the dark side. Finally, we look to the future of seismology. Tidal forces can trigger quakes. The speed at which seismic waves travel through diamond is roughly twice as fast as through silicate rock. If we can detect the ringing of a planet after a violent tidal event, perhaps caused by a flare or orbital resonance, the frequency of the vibration would reveal the internal composition. In conclusion, the concept of a diamond planet sounds like the setting of a science fiction fantasy, a world of infinite wealth. But the reality is far more formidable. These are worlds born of stellar death or chemical anomaly, forged in the crushing gravity of pulsars and red dwarfs. They are not sparkling gems to be mined, but alien engines of heat and pressure. Gravitational tidal distortion acts as the sculptor, kneading these worlds into impossible shapes and powering their internal fires. Carbon crystallization acts as the hardener, turning their mantles into the stiffest structures in the universe, allowing them to survive orbits that would shred a lesser world. Together, these forces tell a story of survival and transformation, reminding us that the universe is capable of creating wonders far stranger and far harder than anything we could dream of on our soft, blue, silicate home. Thank you for listening to G Fun Facts Online.